Good evening, everyone. I'm Jane. I'm a second year PhD student studying mathematics. I'm working on active cloaking, but the coolest way to describe what I do, and my supervisor is going to cringe, is I build invisibility cloaks. So, invisibility has long captivated our imaginations. It's a resident idea in sci-fi and popular culture. We have all heard of Harry Potter's invisibility cloak, and it's probably the first and last time that Predator will feature in one of my talks. But since 2006, there have been a group of researchers who have wanted to transform science fiction into real science. And it started with these two gentlemen. Now, in 2006, they both published a paper in Science. They both published two papers, and they appeared one after the other. And they were working on what's called cloaking. But since 2006, there's been a huge growth in the field, and there's a huge interest in cloaking and invisibility. And if you look at papers, there is over 200 articles with cloaking involved in their titles. Now, I work, because, well, this field of cloaking is so huge that I actually work on a field called active cloaking. So I usually use what's called active sources to cancel out scattered fields. One quite nice example, and you'll be pleased to know, is that you can actually buy invisibility cloaks. Bose created noise-cancelling headphones, and these technically make your ears invisible, but to sound waves. Because how they work is in the earpiece, there's a microphone, and that microphone picks up background noise. And that microphone then tells electronics, electronics that's in the earpiece, it tells a speaker to play a sound wave that exactly cancels out that background noise. So I think you can use them without music, so you can cancel out and have silence around your ears. Or if you're playing music, you'll just hear that, you'll be listening to your tunes and you won't be disturbed and you won't hear any background noise. So effectively, your ears are invisible to the outside world. Okay, so I deal with active cloaking in plates. So the first thing is, what is a plate? Well, I've got my trusty plate here. It's something which the length and the width is much bigger than the width. The height or thickness. And what I do with this plate is I move one side up and down, and what happens is a wave travels through the plate. So it's like, imagine making your bed. If you hold both ends of the duvet and shake it, a wave will go through your duvet. So anyway, as you can see here on this plate, I've drawn a line. And what's happening is when I move the plate up and down, all the particles in this line move up and down together. So that's why we call it a plane wave. And the direction that the wave moves in, so here we've got a nice animation. I'm quite proud of it, but I did steal it from the internet. It took a lot of effort to try and put it in this presentation. What you can see here is that the particles are moving at right angles to the way that the wave is traveling through the plate. And here on the right, this is what's called a contour plot, and it basically tells you you're looking at a bird's eye view of the plate. So it plots different heights that particles in the plate are at. So as you can see, some particles are at different heights as you're going through. But if I look at it side on, that's what you're seeing here. So the lines, the red lines, are the peaks and troughs of the wave. Okay, so that's a plane wave moving through a plate. Now, if I drilled a hole in the middle of that plate and clamped it, so it doesn't move, or if I hammered a nail into that plate, when I send the plane wave through it, we get this horrible looking scattering pattern because that wave comes and hits the object and is scattered around the place. And here we see what's called a shadow region. And that is, well, it can be thought of as the wake of a ship in water. So around here you see water waves, but then behind the ship you don't really see much disturbance. And it's very similar to what's going on here. So around the plate you can see that there's lots of scattering going on, but then here the plate isn't moving very much. And that's the main indication that there is something in that plate. So, I did say that I was going to unveil some maths behind cloaking, but don't be disheartened, these do look like horrible equations. I also thought that when I first saw them. But they are just describing what's happening in the plate. So, the only thing I want you to take away from this is that AN and BN are the incident wave coefficients. So they describe that plane wave that's coming through the plate and is hitting the object. And EN and FN are the scattered wave coefficients. So they tell us how that wave is scattered from the object. And the thing that is really nice is that we can write this equation, which tells us, it's an equation telling us that for any incident wave, so it could be any type of wave, but we mainly deal with plane waves, we know how it's going to be scattered if we pre-multiply by what's called the scattering matrix. Now these are all really well-known equations, but these are the building blocks that we've used to build our cloaks. Okay, so now I've set up the problem, how do we actually cloak? So if you saw before, we had this horrible scattering pattern. Now, to cloak it, we want to make that object look invisible. So what we want to do is try and get this pattern, so that it looks like a plane wave is travelling through the plate and is undisturbed. So how do I do that? Well, what if I push my plate? So imagine that I've nailed it in the middle. What happens if I push this plate with certain frequencies and intensities around the object? Well, I can actually cancel out that scattered wave depending on how hard and how fast I push the plate. So how do we do that? Well, the act of pushing the plate is represented by these, which are called point sources. So they effectively look like ripples happening through the plate. And we write a new set of equations. So now our incident wave coefficients AN and BN not only describe the plane wave that's coming and hitting the object, but also the ripples that are travelling towards the object. And that's what we see here. This is the total propagating wave travelling away and scattering from that object. Here it's a cylinder, but just think of it as the object that's in the plate. And as long as we take into account that that's our new instant wave, we can work out our scattered field coefficients, EN and FN. But also, we worked out our scattered wave, and that takes this part of this equation here. But if we add to it the parts of the wave which are travelling away from the object, and set all of that equal to 0, we actually cancel out that horrible scattered field that we saw before. And it should leave behind just the plane wave. So even though we've got an object in the plane wave will travel through the plate as though nothing's there. In fact, the object is invisible. And that's what we see. This is quite a nice result. So before we had that horrible scattering pattern, and this is the lovely plane wave. But here we have the object surrounded by what we call those active sources. So the large dot is the object, and the small points here are where we push the plate. And solving those equations that I showed you before, or just talk through briefly. And we've actually managed to recreate that plane wave, and you can see that this pattern really does follow this pattern very well. So possible application of this is, if you look here, there's a quiet region around that object. A possible application could be earthquake protection. So maybe we could protect buildings from seismic waves by producing waves which, through our active sources, would cancel out that dangerous wave that could damage buildings. And so, based on that, I'd just like to thank you for listening and hope you understood what I said.